Hello, you are listening to Pankaj Rai, and in this video we will be discussing the numericals of the chapter Chemical Kinetics. So let us begin with average rate. Now, the average rate is given by change in concentration divided by change in time. So the change in concentration would be in molarity and the change in time would obviously be in seconds. So unit of average rate is molar per second. Now average rate is denoted as delta C by delta T. Okay, and we also have something called as instantaneous rate, and instantaneous rate is denoted by dC by dt. Let me take an example. Let's say that A is getting converted to B. Okay, so what is the average rate of consumption of reactant A, because A is getting consumed? So it is given by change in concentration of A upon change in time. Now as the reactant is going on as the concentration of reactant is going on decreasing because it is getting converted to product, so final reactant minus initial reactant would be a negative quantity. So change in concentration of A or the reactant would be a negative quantity, so we just introduce a minus sign here to get the rate as positive. So average rate of consumption of reactant is given by minus change in concentration upon change in time. Now what about average rate of formation of B? It is given by change in concentration of B upon change in time. Now as the A is getting converted to B, so the concentration of B is going on increasing, so final concentration minus initial concentration would be a positive quantity only, so we need not introduce a minus sign here, so we simply write plus. Okay, so this is very simple, that if A is getting converted to B, average rate of consumption of A is minus delta A by delta T, and average rate of formation of B is plus delta B by delta T. Now what about the average rate of the complete reaction? So we have to also mention the average rate of reaction. Now in this case, as you can see, as A is getting consumed, at the same rate B is getting formed, and that actually is the rate of reaction. So rate of reaction in this case can be measured or can be represented in either of the terms, like rate of reaction is same as rate of consumption of A, which is also same as rate of formation of B. So average rate of reaction can be written as minus change in concentration of A upon change in time, which is also same as plus change in concentration of B upon change in time. Just in case if you have to mention instantaneous rate of consumption or formation or reaction, you just have to replace delta by D, and that would be the instantaneous rates. Now let us move ahead. Let me take an example. Okay, let's say that nitrogen gas is combining with 3 molecules of H2 gas and giving us 2 molecules of ammonia, NH3. Okay, so let us focus on this reaction. Now what about the rates of consumption and formation here? So let us write them. So I'll say that average rate of consumption of N2 is minus, because it is rate of consumption, change in concentration of N2 upon change in time. It is so simple. And similarly, we will have average rate of consumption of hydrogen gas is minus change in concentration of hydrogen upon change in time, and average rate of formation of ammonia, that is NH3 is plus of change in concentration of NH3 upon change in time. As simple as that. But so these are the rate of consumption information, but what about the average rate of reaction? Okay, so we have to see about that thing. Now try to concentrate on the reaction. Okay, now if you see carefully, for every one molecule of N2 we are having 3 molecules of H2 which are reacting. Okay, so we have that if let's say 100 molecules of nitrogen gas are getting consumed, so at the same time 300 molecules of hydrogen gas are getting consumed. So rate of reaction of hydrogen is obviously 3 times the rate of consumption of N2. So let me write that rate of consumption of hydrogen, so which would be minus change in concentration of hydrogen with respect to time is actually 3 times, so I'll say minus 3 times rate of consumption of N2. So it is change in concentration of N2 upon change in time. And similarly, if I compare the rates of N2 and NH3, I can see that for every one molecule of N2 consumed, we are getting 2 molecules of NH3 produced or formed. So I'll say that NH3 is getting produced at twice the rate faster than N2. So I'll say that we are having the rate of formation of NH3, so that will be plus of change in concentration of NH3 with respect to time is double, that is twice of rate of consumption, so it is minus 2 change in concentration of N2 upon change in time. Okay, so this is the relation between different concentrations. Okay, you can also form the relation between this and this as well. Okay, but that will come in some time. Now let us move ahead. What about the rate of formation, the rate of reaction of the complete reaction? Now as you can see, the different constituents here, the reactants and the products, are getting consumed and formed at different rates, but the average rate of reaction has to be same irrespective of in what term are we representing it. As in this case, we have the average rate of reaction represented in form of concentration of A, and in this case the average rate of reaction is represented in the form of B. So here, what if I have to represent the rate of reaction in terms of N2 or H2 or NH3? It has to be the same irrespective of their different rates of consumptions and formation. So the average rate of reaction, the average rate of reaction is given by the rate of consumption of a reactant or rate of formation of a product divided by its coefficient. So let me first write it. It is given as minus 1 by 1 change in concentration of N2 with respect to time. Also it is given by minus 1 by 3 change in concentration of H2 with respect to time. It is also given as plus of 1 by 2 change in concentration of NH3 with respect to time. Now, if you remember that the hydrogen was getting produced at 3 times faster rate than N2, okay, so average rate would, let's say we are taking average rate which is equal to the rate of consumption of N2. So average rate is in terms of rate of consumption of N2, and it could be said that it is 1/3 of rate of consumption of H2, because H2 was 3 times faster, so average rate would be same here. And also we saw that the rate of formation of NH3 is double the rate of consumption of N2. So average rate of reaction itself, if we are representing in terms of N2, so it would also be half of rate of formation of NH3, because NH3 was double of N2. So this is the simple way to represent the average rate of reaction. The average rate of reaction is given by 1 by coefficient of the in the chemical, in the balanced chemical equation of the concentration of the reactant or the product. Okay, so that is the simplest way to represent average rate of reaction. Now if you remember, just now we have compared the rate of H2 and N2. It can be seen here as well. See, what if I send 3 over there, so this will become this. Okay, and what about this one and this one? Look at the first one and the third one. If I transfer 2 from here to here, you will get this. So as I said that this is the relation between different concentrations, and we will discuss about the relation between the concentration of H2 and NH3. You can find by this equation. Okay, you can send 2 over here and 3 over here, and you can get the relation between the formation of NH3 and consumption of H2. Okay, now let us move ahead with the numericals. Okay, so as you can see here that we will be discussing two numericals. Okay, so let us begin with the first one. These are the solved examples of your textbook. Now look at this reaction, this question. We have to consider a reaction which is saying that 2N2O5 is getting converted to 4NO2 plus O2. Okay, fine, this is a reaction. Any reaction could be there, it doesn't matter what it is. Now what they are giving, at a particular moment during reaction, N2O5 disappears at a rate of this. So we have been given the rate of N2O5, so that would be the rate of consumption of N2O5, and it is given at a moment. So what do we mean by at a moment? That it is instantaneous rate. Okay, so we have to represent it by d by d. Okay, so we have been given the instantaneous rate of consumption of N2O5. So let me write that instantaneous rate of consumption of N2O5, so it is written as minus d change in concentration of N2O5 upon change in time, and it is given by 0.02 molar per second. So that is the instantaneous rate of consumption of N2O5. But what are we supposed to find? We have to find the rate of formation of NO2 and also the rate of reaction. Okay, so this is a special type of sum, or a type of sum you can say, which always repeats, wherein they give you a reaction and they give you the rate of either one of the component, and they ask you to find the rate of other components. It is very simple, as we have seen in theory that we can compare the rate of reaction. So you can simply say that let's say the instantaneous rate of reaction, the instantaneous rate of reaction can be written to be, as if you remember, it can be written as minus 1 by 2 change in concentration of N2O5 upon change in time. It is also equal to plus 1 by 4 change in concentration of NO2 upon change in time, which is also equal to, here you can see it is only 1 by 1, so it will be 1 only. It will be change in concentration of O2 upon change in time. So this is the equation which is giving you relation between different rates of the different components of reactants and products. Okay, so what they have given to us, they have given to us that this rate, this one, is 0.02. Okay, so it is very simple. Now if you substitute 0.02 over here, so this is 0.02, and if you have to find the rate of NO2, let's say we are finding that rate of let me write it again. So let's say we have to find that rate of formation of NO2 upon time with respect to time is, you can say, 4 by 2 minus 4 by 2, so that would be minus 4 by 2, so that will be minus twice the dN2O5 by dt. Now dN2O5 by dt can be written to be, if I send this minus over here, so it will be minus. Okay, so or you can say that minus dN2O5 by dt is substituted as 0.02, so we will write it as, we are sending 4 over there and 4 by 2 is becoming 2, and we are substituting minus dN2O5 dt by 0.02, so that will be 2 times 0.02, so it is 0.04 molar per second. It is so simple. And what about the rate of formation of rate of formation of O2? It, this is exactly equal to this one, so it is minus half, that is half of this, so I can say it is half of 0.02, so that will be 0.01 molar per second. So this is what we have been asked, the at what rates NO2 and O2 are formed, so we have answered that. Now the final question is, what about the rate of reaction? The rate of reaction can be found out by substituting any of the value. If we say, let's say we are substituting this value over here, so it will be 0.02 upon 2, so that it will be 0.01. Let's say we are substituting this value over here, this value over here, so 0.04 upon 4, so that will again be 0.01. Or let's say we are finding the rate of reaction by using only this, so that is equal to 0.01. So in either of the case, the rate of reaction is 0.01 molar per second. So in this way you can solve such numericals. Okay, now let us move ahead with the next numerical and let's see what is there. We are having here that nitrogen dioxide, which is NO2, is decomposing to give us nitric oxide NO and molecular oxygen O2. Fine. Now we have been given concentration time data for NO2. Okay, that is only for this. We have been given NO2 at 300 degrees Celsius. For 300 degrees Celsius actually should be. So time in second and concentration of NO2 in molarity. So at 0 time, that is at the start of reaction, we are having 8.4 into 10 raised to minus 3 molar of the concentration, and as and when the time will increase, the concentration of the reactant will go on decreasing and the concentration of products will go on increasing. Okay, now calculate average rate of decomposition of NO2. Okay, so if you see here, we have to find the average rate, okay, over a duration. This was the instantaneous rate, at a particular moment it was given. Okay, the rate was given, and here we have been given the concentrations at different times, so we don't know exactly what is the instantaneous rate, but we can find average rate over duration of time. So what are we asked is, calculate average rate of decomposition of N2 and average rates of formation. Okay, that is same. If we can find this, we will be able to find these two, but during the time interval 200 second to 300 seconds, so we have to find during this time interval the average rate. Okay, and find what is the average rate of reaction. It is same question. The only thing which we have to do is we have to find the average rate first of all of NO2. Then we would be able to find this one, then this one, and also the rate of reaction. That would become same as this. Okay, so let us move ahead and let us try to find the average rate of decomposition of NO2. Now let me write here. Let's say we are writing average rate of decomposition or consumption of NO2. It would be given by minus, because it is consumption, delta NO2, that is change in concentration of NO2, upon change in time, that is the basic formula for consumption. Okay, and that is equal to minus of, now here I have to write the concentration at 300 second minus concentration at 200 second upon 300 minus 200. Okay, so here I have to write the concentration at 300, so it is 3.0 into 10 raised to minus 3 minus concentration at 200 second, so that is 4.3 into 10 raised to minus 3, and divided by change in time, so it is 300 minus 200. Now this quantity would come as negative. It is coming out to be minus of, this is coming out to be minus 1.3 into 10 raised to minus 3 upon, and this is 100 seconds. So minus of minus will become plus, so it is 1.3 into 10 raised to minus 3, and this 100 will go up, so it will actually become 10 raised to minus 5. So that is the average rate of decomposition of NO2, that would be in molar per second. So let me write it here, that we have just got the average rate of decomposition of NO2, and it is coming out to be 1.3 into 10 raised to minus 5 molar per second. Okay, now so we are able to find now the average rate of decomposition of NO2. Now this question at this point of time is similar to the previous question, wherein you have been given the rate of one of the component and you were supposed to find the rate of other components and also the rate of reaction. So similarly now we have been given, that is we found out the rate of consumption of the reactant, and we would be able to find out the rate of formation of products by using our equation. Average rate of reaction is equal to minus 1 by 2 change in concentration of NO2 upon change in time, which is same as plus 1 by 2 change in concentration of NO upon change in time, which is also same as change in, sorry, this is change, so change in concentration of O2 upon change in time. Okay, now let's say we have to find the rate of formation of NO, so it would be the rate of formation of NO is equal to, if we use these two, so 2 will get cancelled and this will be equal to minus change in concentration of NO2 upon change in time, and that is, we just found out that minus delta NO2 upon delta T is 1.3 into 10 raised to minus 5. So this will also be 1.3 into 10 raised to minus 5 molar per second. Now what about the rate of formation of O2? So rate of formation of O2 from this one, when equated to this, it comes out to be minus half of change in concentration of NO2 upon change in time. But the value of minus delta NO2 upon delta T is this, and we have to take half of that, so that will be the half of 1.3, which will be 0.65, so it is 0 0.65 into 10 raised to minus 5 molar per second. Okay, what about the rate of reaction? Okay, so rate of reaction is either of this, either the first one or the second one or the third one. As you can see, the rate of reaction is equal to the rate of formation of O2 directly, so we can write that it is 0.65 into 10 raised to minus 5 molar per second. So in this way you can solve numerical based on the rate of reaction or rate of consumption or rate of formation. Thank you very much.